On November 22nd, the interstellar comet 3I Atlas was captured by NASA from almost every angle. But behind those perfect images are things they are not fully telling us. From a faint streak in stacked frames, 3I Atlas emerged with a hyperbolic trajectory that will pass through the solar system only once a small icy nucleus, with unusually strong activity, an abnormally high CO2 ratio, strange nickel signatures, and a lack of long carbon chains, all hinting at a very distant origin, and an extremely long journey between the stars. When Earth was hidden during perihelion, an entire orchestra of spacecraft, from Mars orbiters to solar observatories and asteroid missions, was mobilized to lock down its orbit and scrutinize the tail coma hydrogen and multi-layered tail structure of 3I Atlas. NASA publicly insists that this is just a comet, but for skeptical scientists, the large-size early strong activity, seemingly well-timed trajectory, teardrop shape, and unusual spectrum of 3I Atlas are challenging all familiar models. Whether Atlas ultimately proves to be completely natural or not, its scientific value remains priceless. And right now, we're about to explore the latest mysteries of Atlas's strange structure and anomalous activity. On quiet nights at the observatories long before anyone spoke the name 3, I Atlased aloud, rows of digital images were already waiting in archived folders. Astronomers would later return to those silent frames and realize that Atlas had been passing across them like a barely noticeable smudge of moving light. Each exposure showed only a faint point, almost indistinguishable from the background stars, so the teams began to align and stack dozens of frames into a single composite view. In that combined image, Atlas slowly separated from the sky like a whisper pulled out of noise, revealing a path rather than a fixed star. The technique turned time into depth, letting the motion of 3 at last appear as a thin streak while the stars stayed still. Researchers watched that streak with careful eyes, hoping that subtle changes in brightness might betray a hint of rotation. They knew that if at last were spinning in a simple way, small rhythmic variations should ripple through the light as the nucleus turned. Instead, the growing cloud of dust around Atlas spread and softened the signal, smearing away the fine structure that rotation would create. The coma that made the comet so beautiful also masked the heart of Atlas from their measurements. What remained in those early data was a paradoxical impression of motion, without a clear spin like a dancer glimpsed only through drifting fog. For the scientists, this quiet puzzle became the first invitation to look closer at 3I Atlas in the nights ahead. Within days of the discovery alerts, infrared observatories quietly turned their mirrors toward 3 Atlas, searching for the faint warmth of hidden ice. Gemini South and a dedicated NASA infrared facility watched the glow around Atlas rather than the nucleus itself, measuring how starlight and sunlight were scattered by the expanding cloud. In those wavelengths, the teams found a signature that matched water ice changing phase, a gentle exhalation, suggesting that Atlas was releasing vapor into space. The detection meant that 3 Atlas was not only reflecting light, but actively responding to the sun, building a coma from ancient frozen material. To understand the solid body beneath that haze, astronomers turned to the sharp vision of the Hubble Space Telescope and framed the distant visitor against the background stars. Even Hubble could not fully resolve the core of Atlas, yet the tiny unresolved point placed a strict ceiling on the possible size of the nucleus. From that limit, the teams concluded that the central body of 3I Atlas was no larger than a few kilometers across, tightly wrapped inside its own halo. Using the brightness of the dust envelope, researchers estimated that Atlas was shedding tens to hundreds of kilograms of material every second into the surrounding void. Each grain of dust leaving the surface carried away a trace of the world that formed 3 Atlas like sand falling from a slowly opening hand. For those watching from Earth, these early measurements turned Atlas from a mere moving dot into a living source quietly evaporating as it crossed the inner darkness. When the James Webb Space Telescope finally turned toward 3 Atlas in early August, the observatory was not just taking a picture, but listening for the chemical voice of a visitor between the stars. Webb spread the light from Atlas into a spectrum, a delicate barcode of wavelengths, where every dip and rise told of a different molecule shimmering in the coma. Among the familiar fingerprints of water vapor, the instruments found another presence standing out with unexpected strength, a broad signature belonging to carbon dioxide that wrapped 3 Atlas like a cold, invisible veil. When the numbers were gathered, the ratio was startling, roughly 8 parts carbon dioxide for every 1 part water, a proportion far from the patterns usually seen in comets born near our own sun. For scientists used to more modest levels of this gas, ATLAS seemed to be broadcasting a composition that did not quite fit into the shelves of existing models. Some researchers wondered whether 3 Atlas had formed in a region of its home system, unusually rich in carbon dioxide, a kind of distant frozen reservoir. Others considered a longer story where Atlas had drifted through interstellar space for so many ages that lighter elements slowly escaped, leaving the heavier gas behind to dominate the spectrum. In meeting rooms and late-night calls, curves from the Webb data were compared with catalogues of other comets, and 3 Atlas kept refusing to blend in. The anomaly did not break any law of physics, but it nudged against expectations as if at last were hinting at environmental conditions rarely sampled before. Quietly, the discovery marked a turn in the narrative, guiding astronomers from simple confirmation toward deeper questions about where 3I Atlas began its journey and how long that journey has been. Long before anyone on Earth spoke of spectra and ratios, theorists were already sketching possible birthplaces for 3 Atlas across maps of distant planetary nurseries. One family of ideas placed Atlas in the outer reaches of a foreign star system where carbon dioxide could condense in abundance and freeze into the bulk of a small wandering world. In that imagined cradle, 3 Atlas would have grown slowly from grains and pebbles, locking away volatiles in layered ice, while its parent star was still wrapped in a disk of dust. A close encounter with a giant planet or passing star could then have given Atlas the final push, hurling the young comet clear of its home and into the deep interstellar dark. Another line of thought treated 3 Atlas less as a youth and more as an elder, a relic that has drifted between the stars for untold hundreds of millions or even billions of years. During such a prolonged journey, the outer layers of Atlas would repeatedly feel the faint warmth of distant suns, gentle tidal tugs, and the thin rain of cosmic rays. Over time, lighter components might slowly escape from the surface of 3I Atlas, leaving heavier gases and more stable structures to dominate what is left to observe today. For the scientists modelling these scenarios, both pictures came with uncertainties and compromises, and no single story wrapped cleanly around all the measurements drawn from Atlas. In the quiet space between equations, 3 Atlas became a traveller whose age and origin could be sensed but not yet pinned down, like a voice heard through a long echo. That lingering ambiguity set the stage for later chapters of the investigation, where motion shape and subtle anomalies in the path of Atlas would offer new clues to its past. Just when researchers thought they were beginning to understand the chemistry of 3 Atlas, a different kind of surprise emerged from the detailed spectra. In the glow around Atlas, instruments picked up clear signs of nickel, a heavy element that usually appears hand in hand with iron in cometary environments. This time, the balance looked skewed, as if the comet Atlas were displaying nickel more readily than the iron that typically shares the same shelves in cosmic storage. While calibration checks and comparison stars were examined carefully, the early patterns still suggested that 3 Atlas carried an unusual metallic fingerprint in its surrounding gas. At the same time, another quiet anomaly appeared in the data, this one tied to carbon-bearing molecules. Lines associated with long carbon chains seemed weak or scarce, pushing chemists to consider that Atlas favoured simpler carbon structures over the complex chains familiar from many comets. One possible reading of this pattern was that 3 Atlas formed in a region where long organic chains never accumulated in large amounts. Another possibility was that the long journey of Atlas through interstellar space had gradually stripped away the more fragile molecules, leaving a more distilled mixture behind. Later observations closer to the Sun began to reveal more iron, softening the initial contrast, but not erasing the memory of that early metallic oddity around 3 Atlas. For teams tracing the story in these subtle imbalances, each new spectrum turned Atlas into a more layered character, holding back parts of its history while quietly revealing others. While observers on Earth were preparing for a period of blindness near perihelion, another stage quietly opened around Mars as 3I Atlas crossed that distant neighbourhood. From orbit, the ExoMars Trace Gas Orbiter had a vantage point that no telescope on the ground could match, watching Atlas against a thinner, steadier sky. Engineers adjusted pointing sequences so that the instruments normally devoted to sniffing Martian gases could briefly turn outward toward the passing visitor. In those carefully planned windows, ExoMars gathered frames where 3I Atlas appeared as a moving point beyond the rust-coloured limb of Mars, a tiny spark drifting through blackness. The geometry of the encounter gave ExoMars and companion orbiters a wide separation from Earth-based lines of sight stretching the triangle of observations around 3I Atlas. With that extended baseline, navigators could refine the path of Atlas, more precisely tightening the uncertainties that still surrounded the interstellar trajectory. Each new position measurement became a small anchor in space, helping scientists test whether the motion of 3I Atlas followed expectations for a large active comet. Any persistent deviation from those expectations would have stood out more clearly when triangulated between Earth, Mars, and the track drawn through the inner system. For planetary defense specialists, the cooperation between agencies around Mars turned 3I Atlas into a rehearsal for future uninvited guests. For those focused on the mystery, the scenes from ExoMars added another quiet layer to the story, showing Atlas as a wanderer seen from yet another world. In mission logs and nightly briefings, the presence of 3I Atlas near Mars became a reminder that the solar system is now watched from more than one shore, and that future visitors will be traced with growing confidence. As 3I Atlas moved through the Martian sky, another observer beyond ExoMars quietly stepped forward, a spacecraft designed to listen in ultraviolet rather than visible light. MAVEN, circling Mars for years to study the upper atmosphere, repurposed its imaging ultraviolet spectrograph to stare outward toward the faint glow around Atlas. In those ultraviolet wavelengths, hydrogen around 3 Atlas revealed itself as a soft emission, a pale halo laid over the darkness beyond the planet. The challenge was that hydrogen also surrounds Mars and drifts through interplanetary space, so MAVEN had to disentangle 3 overlapping sources of the same gentle light. By measuring differences in direction, altitude, and timing, the team separated hydrogen escaping from Mars from the broader background, leaving a component that traced directly back to Atlas. That remaining signal became quiet evidence that 3 Atlas was releasing water, its vapor broken apart by sunlight into atoms spreading far beyond the visible coma. Closer to the ground, another vantage point waited, this time on the dusty floor of Jezero crater, where the Perseverance rover worked beneath a salmon-coloured sky. Engineers commanded the rover to lift its mast cam toward the thin air, searching for 3I Atlas as a tiny moving fleck above the Martian horizon. In the processed images, after contrast was stretched and noise suppressed, a faint streak appeared, a small mark that matched the predicted path of Atlas. The picture was not dramatic, yet the idea of seeing 3 Atlas from the surface of another world carried a weight that numbers alone could not. Together, the hydrogen glow from MAVEN and the quiet streak from Perseverance turned Atlas into a shared reference point between orbit and ground, binding multiple perspectives into one widening story. Far from Mars and the rovers, another group of watchers followed 3 Atlas from positions tuned to the changing moods of the Sun. SOHO, long stationed between Earth and the Sun, recorded Atlas as a faint newcomer, wandering through fields usually reserved for solar storms and coronal eruptions. In SOHO movies, the bright mask of the Sun was blocked, and 3 Atlas slid slowly across the frame, while background stars held their fixed grid. The growing tail of Atlas stretched away from the Sun, shaped by light pressure and solar wind, outlining invisible forces in pale drifting geometry. Punch and the stereo spacecraft added new angles, giving 3 Atlas depth rather than a single flat track. From those differing lines of sight, the changing brightness and apparent direction of Atlas could be woven together, turning scattered images into a 3-dimensional sense of motion. Researchers traced the way the tail of 3 Atlas kinked and swayed as gusts of solar wind passed, watching the comet behave almost like a weather vane in a cosmic breeze. Farther out, the Psyche and Lucy missions contributed their own serendipitous views, catching 3 Atlas from locations well away from both Earth and Mars. Each detection of Atlas from those asteroid explorers gave one more anchor point, one more precise timestamp and position in the interstellar trajectory. With every added measurement, the path of 3 Atlas grew sharper, the uncertainties narrower, and the sense of a coordinated solar system chorus stronger. For scientists piecing together this mosaic, Atlas became a quiet center of attention, a single visitor seen from many shores guiding the story toward more tightly constrained models and deeper questions. The announcement of the briefing came with little warning, a simple notice that NASA would address a newly arrived interstellar visitor and share fresh images from deep space. Journalists, mission scientists, and engineers gathered in the hall, and on video links feeling the quiet pull of history as displays behind the speakers, prepared to show the first close looks at 3I Atlas. For many watching from home, the name Atlas still meant only a streak in a diagram or a line in a news article, but the tone of the invitation suggested something larger, Staff speaking before the main presentation reminded the audience that only 2 other confirmed interstellar objects had ever crossed the solar system under human observation, making the arrival of 3 Atlas a rare 3rd chapter in a very short book. When the briefing began in earnest, the first images appeared on screen, processed frames, from orbiters, coronagraphs and telescopes all converging on a single faint structure wrapped in a luminous haze. Narrators explained how Atlas had been traced from the outer system inward, its path reconstructed from observations scattered across weeks and millions of kilometers. Graphs followed the images showing how brightness changed with distance, how the coma of 3I at last expanded, and how gas and dust production compared to familiar comets of the inner system. The presenters did not claim certainty, but they spoke of potential, emphasizing that Atlas offered the first extended coordinated campaign on an interstellar comet with strong activity. Slides outlined how data from 3I Atlas could refine models of how small bodies form around other stars and how interstellar space slowly sculpts their surfaces. In the room, there was a shared awareness that future textbooks might one day reference curves and figures first shown in this briefing, quietly tying Atlas to the broader arc of planetary science. As the session moved toward questions, the tone shifted from unveiling to reflection, and the speakers invited listeners to see 3. Atlas not as an isolated curiosity, but as the opening move in a new era of studying visitors from beyond the Sun's immediate family. When orbital computers first stitched together the early measurements, the path of 3A Atlas refused to close into any familiar loop around the Sun. Instead of forming an ellipse like the planets, or a stretched oval like long-period comets, the track of Atlas unfolded as a hyperbola, a curve that opened outward toward interstellar space. On the diagrams in mission rooms 3, Atlas appeared as a visitor on a one-way trajectory, falling in toward the Sun only once before departing forever into the dark. At first, this shape fit the simple story, another interstellar body like those seen before briefly cutting through the solar system. Yet as more points were added, small discrepancies began to show in how closely Atlas matched the expected brightness and activity for a comet following that path. Some models predicted that a body the size of 3I Atlas should respond more gently to sunlight at large distances, while the real Atlas already showed a surprisingly vigorous coma far from perihelion. Mission analysts recalculated using different assumptions about mass density and gas production, trying to see whether a normal comet could still carry the behaviors that Atlas displayed. The hyperbolic shape remained, but the fine details of the track seemed delicately sensitive to how strongly 3I Atlas pushed back against gravity with its outflowing gas. In that sensitivity, researchers sensed the possibility that subtle non-gravitational forces might slightly tweak the journey of Atlas, just as they had argued about other interstellar visitors. For now, the official plot still showed a clean open curve for 3 Atlas, a graceful escape route past the Sun. Behind those smooth lines, however, the early anomalies encouraged scientists to keep testing whether the motion of Atlas was entirely ordinary or quietly hinting at deeper complexities to be uncovered in later data. As the date of perihelion drew closer, planners confronted an uncomfortable fact during the critical days when 3 Atlas would skim nearest to the Sun. Earth itself would be hidden on the far side blind behind the solar glare. Rather than accept that blackout mission, teams began to map every spacecraft with a usable camera or spectrometer that was not tied to Earth's line of sight. Lists appeared on whiteboards and shared documents, each line naming a probe that could be turned even briefly toward Atlas. In those early meetings, 3 Atlas moved from being just an object of interest to becoming the center of a coordinated campaign. Solar observatories, Mars orbiters, and asteroid missions were all considered some far from their original purposes, but still capable of seeing Atlas from a unique angle. Engineers calculated how long instruments could safely steer away from their primary targets, how much pointing fuel remained, and whether each detour would fit inside tight mission margins. The emerging plan treated 3I Atlas as a test of what the modern solar system network could do when it acted as a single distributed observatory. No one spacecraft carried the whole responsibility. Instead, Atlas would be followed in a relay of overlapping views, each one adding depth to the shared picture. For the scientists watching the plan come together, this was more than a logistical exercise. It was a quiet statement that 3 Atlas mattered enough to bend routines, to synchronize distant machines, and to prove that the next interstellar visitor would not find humanity watching from only one vantage point. With the campaign agreed upon attention, began to shift toward the first detailed images that these repurposed eyes would soon return from their scattered posts. From high above Mars, the Mars Reconnaissance Orbiter turned its sharp camera away from the planet and locked onto the faint speck of 3I Atlas. In a series of long exposures, the background stars stayed as precise points, while Atlas showed a slightly swollen core wrapped in a hazy glow. Even at 19 million miles, the image revealed that 3 Atlas carried a compact bright center hidden inside a soft expanding coma. Mission teams processed the frames, carefully subtracting scattered light from Mars and the Sun until the outline of Atlas stood out more clearly against the dark. The refined pictures allowed scientists to measure how large the inner envelope of dust had become and how sharply 3 Atlas brightened toward its center. Meanwhile, MAVEN adjusted its orbit and instruments, turning from the Martian atmosphere toward the same distant visitor, 3 Atlas. Using ultraviolet sensors, MAVEN measured the thin shimmer of gas around Atlas, looking for signs of hydrogen and other products of water loss. Together, the optical clarity of MRO and the spectral sensitivity of MAVEN gave 3 Atlas a kind of close-up portrait drawn from 2 complementary senses. For researchers piecing together the story, these views from Mars orbit marked a turning point, when Atlas ceased to be just a plotted object and became a clearly resolved presence moving through shared space. On the floor of Jezero crater, the Perseverance rover followed its usual routines, examining rocks and dust under a pale Martian sky. Then a new command sequence arrived, asking Perseverance to pause its local survey and lift its Mastcam toward a patch of thin atmosphere where 3 Atlas was predicted to pass. Engineers on Earth had traced the path of Atlas across the Martian sky, turning those calculations into a quiet request for the rover to look up at just the right time. The raw images returned by Perseverance looked almost empty at first, a scatter of weak stars and sensor noise above the crater rim. Only after careful processing did a faint streak emerge, a tiny line that matched the expected motion of 3 Atlas from one frame to the next. What Perseverance captured was not a dramatic plume or a detailed nucleus, but the simple, delicate fact that Atlas could be seen from the surface of another world. In mission logs, the moment was marked as a small milestone, a notation that 3 Atlas had been recorded both from orbit and from the ground of Mars. For those who thought about the scene more quietly, the image felt like a bridge linking the wandering path of Atlas to the steady wheels of a rover far from Earth. Under that distant sky, Perseverance became an eyewitness to an interstellar visitor, and 3I Atlas became part of the growing shared history of worlds watching one another. Far from Mars, spacecraft built to study the Sun were also watching, as 3I Atlas drew closer to the inner system. SOHO, staring from its long-held post between Earth and the Sun, recorded Atlas as a dim newcomer sliding through coronagraph frames, usually filled with streamers and eruptions. In those movies, the central glare of the Sun was hidden behind an artificial disk, and 3 Atlas appeared as a soft point, with a faint tail stretching away into the darkened field. From different orbits, the stereo spacecraft traced the same visitor, giving Atlas a second and third line of sight. By comparing how bright the coma and tail looked from each vantage point, scientists could build a more three-dimensional sense of how 3I Atlas was shedding dust and gas. The tail did not stay perfectly straight. Under the pressure of sunlight and the changing gusts of solar wind, the long plume from Atlas kinked, bent and slowly swayed like a narrow flag responding to invisible weather. Punch, designed to image the outer reaches of the solar wind, added still another perspective tracking structures around 3 Atlas as they merged with the flow of charged particles. In those sequences, researchers saw how the tail of Atlas mapped the boundary between calm and disturbed regions of space, revealing small irregularities that models did not always predict. The behavior was not dramatic enough to declare a mystery on its own, but it reminded observers that 3 Atlas was not just passing through a static environment. Instead, Atlas was moving through a living, restless medium, and the way the tail responded helped bridge the story from simple orbit plots toward deeper questions about how interstellar comets interact with the Sun. Farther from the Sun, 2 missions with very different primary goals found themselves in positions to glimpse 3 Atlas from unexpected angles. Lucy, launched to study Trojan asteroids, watched Atlas drift through a star field that was never part of its original science plan. In those frames, 3 Atlas appeared as a slowly moving point among the more static specks of the distant background, giving navigators another precise timestamp and position to feed into orbit models. Psyche, on a separate journey toward a metallic world, also held a camera capable of catching 3 Atlas as the comet crossed its distant sky. From Psyche's vantage, the angle between Sun spacecraft and Atlas differed sharply, from both Earth and Mars, stretching the network of sightlines even wider. The brightness and apparent motion of 3 Atlas from these far-flung platforms helped tighten the uncertainties in the trajectory, reducing small ambiguities that still lingered after earlier campaigns. For the teams managing Lucy and Psyche, turning their instruments toward 3 Atlas was a brief pause from their core missions, yet the added data rounded out the growing mosaic. In the combined plot of all observations, the extra points from Lucy and Psyche made the path of 3 Atlas look less like a sketch and more like a carefully inked line. That clarity set the stage for the next part of the story, where attention would shift from where Atlas was going to what the official narrative would say about what Atlas truly is. The briefing room grew quieter when a senior NASA official stepped to the podium and mentioned the growing swirl of online speculation about 3 Atlas. Without naming every rumour, the speaker acknowledged that many people were asking whether Atlas might be something more exotic than an ordinary comet. Then, in clear and measured language, he said he wanted to put the rumours to rest, and stated that 3 Atlas is a comet behaving in ways that fit a natural icy body from another star system. Slides appeared behind him, showing light curves, spectra, and model comparisons, all framed to demonstrate how at last matched known patterns, once distance and activity were properly accounted for. The explanation emphasized that 3 Atlas has a coma, a tail ongoing outgassing, and brightness changes consistent with a large active comet under solar heating. Every few minutes, the speaker circled back to the same point, repeating that Atlas looks and acts like a comet, not a spacecraft or engineered probe. For some in the audience, the insistence itself became a quiet point of curiosity, because few briefings explicitly address rumours so directly. Still, the tone toward the end grew more reflective, inviting listeners to focus less on speculation and more on the scientific opportunity that 3 Atlas represents. As the session closed, the official reminded everyone that future data could refine details, but that for now, NASA stood by its conclusion: 3 Atlas is a comet, and studying Atlas deeply is the best way to answer lingering questions. Avi Loeb approached 3 Atlas with the instinct of someone trained to distrust whatever seems obvious. For many colleagues, the presence of a coma and tail made at last a straightforward interstellar comet case closed. Loeb warned that when data feel comforting, assumptions harden too quickly around them. He argued that 3 Atlas should not be granted the label natural by default, but forced to earn that status through careful testing of every anomaly. In public essays and quiet seminars, Loeb asked whether Atlas might expose blind spots in current models. For him, the real danger was not that 3 Atlas hides something extraordinary, but the comfortable explanations keep astronomers from noticing what Atlas is quietly trying to say. From the first estimates of brightness and dust production, 3 Atlas stood out as a surprisingly substantial visitor. Models translating that light into size suggested a nucleus, several kilometers across, a bulk more in line with robust long-period comets than with a fragile wanderer eroded by eons between the stars. Yet at distances where many comets only begin to stir, 3 Atlas was already shedding gas and dust with a vigour that caught dynamicists off guard. Under gentle solar heating far from perihelion 3, Atlas built a large bright coma and a well-defined tail, as though shallow warmth were enough to unlock generous reservoirs below the surface. For a world that may have drifted through interstellar space for immense stretches of time, such responsiveness hinted at pockets of volatile material preserved far better than some theories expected. To reconcile the observations, teams proposed that 3 Atlas might have a composition especially rich in certain ices, or a structure that channels heat efficiently into active regions. Other researchers wondered whether 3 Atlas had simply spent less time in harsh interstellar conditions than assumed, remaining geologically youthful despite the long journey implied by the hyperbolic path. The tension lay in balancing a large energetic nucleus with the idea of an ancient relic, and 3 Atlas refused to collapse neatly into either extreme. In this mismatch, astronomers sensed a clue rather than a contradiction, a prompt to refine how they think about aging, layering, and heat flow in bodies like 3 Atlas. As new data continued to stream in the unusual combination of size and early activity, pushed the story away from comfortable templates, guiding the next questions toward the deeper interior of 3 Atlas and the long history written into that hidden core. Some researchers could not ignore the way the path of 3 Atlas threaded itself through the inner solar system with almost theatrical timing. On one plot after another, the hyperbolic track of Atlas brought the comet close to Mars just when multiple orbiters and a surface rover were ready to watch. Statisticians reminded colleagues that rare alignments do happen by chance, and that among countless unseen objects, 3I Atlas might simply be the one whose trajectory happened to intersect our current web of missions. Modelers ran ensembles of simulated visitors showing that a small fraction would from time to time line up for optimal observation the way Atlas had apparently done. For those drawn to more speculative thoughts, the geometry of 3 Atlas still felt uncomfortably like a path chosen for visibility rather than accident. From that angle, the timing of Atlas passing Mars and sliding behind the Sun during perihelion looked almost like a test of how flexible our observing network had become. To keep the discussion grounded, teams framed the behaviour of 3 Atlas as a spectrum between pure coincidence and purposeful design, with no evidence strong enough to anchor the far end. In that spectrum, Atlas became a reminder that even when randomness is the best explanation, the patterns we notice can push us to ask better questions about how we are watching the sky and how ready we will be for the next visitor. In high-resolution images, the coma of 3 Atlas did not spread as a neat symmetrical cloud. Instead, Atlas displayed a teardrop shape, a bright tapered form that seemed to lean in one direction, as if pushed or venting unevenly into space. Spectra taken alongside those images showed the usual carbon features, but 3 Atlas also carried lines that sat awkwardly against standard comet templates. Some peaks were shifted in strength or position, hinting that Atlas mixed familiar chemistry with conditions rarely sampled before. For observers, 3 Atlas became less like a textbook example, and more like a quiet challenge inviting fresh models to explain its tilted glow. Ground-based images taken after perihelion suggested that the tail of 3 Atlas was not a single simple streamer of dust. In long exposures, some observers reported that one component of the tail from Atlas curved gently along the orbit while another seemed to point more directly away from the Sun, as if guided by different forces. Careful processing hinted that 3 Atlas might carry at least 2, and perhaps 3 overlapping structures, a dust tail pushed by sunlight, a more linear ion tail shaped by the solar wind, and a fainter, more diffuse envelope in between. When spectra were aligned along these features, the signals did not collapse into a single explanation. One section of the tail around Atlas appeared richer, in typical dust signatures, while another showed stronger traces associated with ionized gas. A possible third component remained harder to classify, hovering at the edge of detection and inviting caution in how firmly scientists spoke about it. For modelers, 3 Atlas entered what many called a grey zone, a region where data are good enough to suggest complexity, but not yet sharp enough to settle arguments. Some colleagues urged restraint, insisting that multi-component tails had been seen before and that Atlas likely fits within a stretched version of known comet behaviour. Others pointed out that 3 Atlas is one of the first clearly active interstellar comets with such dense coverage, and that subtle departures from templates might reveal conditions unique to its origin. In this overlap between certainty and speculation, 3 Atlas became a quiet case study in how science proceeds. Rather than rushing to label every feature, researchers let the multi-layered tale of Atlas remind them that living with partial understanding is part of the discipline, and that the next observing window might gently tip the balance toward clarity. From the beginning, scientists understood that the value of 3 Atlas did not depend on whether headlines called Atlas ordinary or extraordinary. Even in the most conservative reading, 3 Atlas represents a physical sample of another planetary system, a fragment of some distant disk that formed planets around another star. Every spectrum drawn from the coma of 3 Atlas adds to that sample, turning faint light into clues about the temperature, pressure and chemistry that shaped Atlas long before it entered interstellar space. Ratios of gases, the presence or absence of certain organic chains, and the metallic signatures seen around Atlas all become constraints on how solids form and evolve beyond the Sun's neighbourhood. At the same time, 3 Atlas refuses to line up perfectly with expectations, from its rich carbon dioxide content to early hints of unusual metallic balance and multi-component tails. None of these traits by itself violates known physics, but taken together they push models toward corners that have not been fully explored, reminding researchers that Atlas comes from a regime of parameter space still sparsely mapped. Because of that, abandoning detailed study of 3 Atlas in favour of a quick label would mean walking away from a rare, well-instrumented experiment delivered by nature. Instead, the community has treated Atlas as a long-term investigation, planning follow-up observations, laboratory simulations, and comparative studies with comets of the outer solar system. For many in the field, 3 Atlas symbolizes a shift from treating interstellar visitors as curiosities towards seeing them as essential data points in a broader theory of planet formation. The more precisely at last is characterized, the better future scientists will be able to place new interstellar objects on a continuum, deciding whether they are typical siblings or genuine outliers. There is also a quieter, more personal dimension to the curiosity around 3I at last. Researchers know that opportunities like this are rare within a single career, and that the decisions they make now about how carefully to measure at last will shape what later generations inherit as a baseline. In that sense, the demand for continued investigation is both practical and philosophical. 3I at last is a reminder that the cosmos occasionally sends pieces of its history directly to our doorstep, and that the proper response is patient, thorough listening. As the comet moves onward along its hyperbolic path, plans turn toward the next major window of observation, when the geometry between Earth, Sun and Atlas will again favour closer scrutiny and new chances to refine the story. As the calendar moved toward December 19th, astronomers quietly circled the date, knowing that 3 Atlas would be closer to Earth than at any other time in this passage. On that night, Atlas would still be far away in ordinary terms, roughly 170 million miles from our planet, yet close enough for large telescopes to gather light with unusual precision. For many teams, this geometry turned 3 Atlas into a rare natural laboratory, a moment when the signal from the coma would be bright and steady enough for delicate measurements that earlier weeks could not support. Plans were drawn up for long integrations on major observatories with spectrographs tuned to tease apart the finest details in the glow of 3 Atlas. Beyond simple abundances, researchers hope to measure isotopic ratios, tracing how heavy and light versions of the same element are distributed within the gases flowing from Atlas. One key target was the ratio of deuterium to hydrogen in the water released by 3 Atlas, a number that quietly encodes the temperature and conditions in the region where Atlas originally froze. Comparisons with comets from the outer solar system would tell whether 3 Atlas resembles local families or carries a distinctly foreign signature. If the isotopic fingerprints of Atlas fall far outside known ranges, models of planet-forming disks may need to expand to include far colder or more varied environments. If the ratios around 3 at last overlap strongly with local examples, the result would still matter, hinting that certain chemical patterns might be common across very different stars. During the nights around closest approach, observatories plan to watch 3I Atlas for subtle shifts in brightness and line shapes, searching for any changes that might betray fresh outbursts or structural evolution. Each clean spectrum from that window would become part of a permanent record, a high watermark in how well one interstellar comet, 3 Atlas, has been characterized. For scientists and students who will one day read those archived plots, the date may appear as a simple label on an axis, but behind that label lies the memory of a world briefly aligned to listen more closely to a visitor passing through. In the quiet years after 3 Atlas has faded from easy reach, its data will continue to work like fingerprints. Researchers will return to spectra light curves and orbit reconstructions, treating Atlas as a case file in a growing archive of interstellar visitors. This slow, careful practice is what many have begun to call forensic astronomy, the art of reconstructing distant histories from scattered clues. In that emerging discipline 3, Atlas stands near the beginning of the catalogue, a well-observed example against which new arrivals will be compared. Every anomaly or pattern around Atlas becomes a reference point, helping scientists decide whether a later object behaves like a sibling or an outlier. As methods improve, Atlas will be reanalyzed with fresh algorithms and better calibrations, revealing details that current tools may be smoothing away. The future of this work is closely tied to the Vera Rubin Observatory, a wide-field telescope designed to scan the entire visible sky again and again. When Vera Rubin begins its survey, the flow of discoveries will change character, with many more transient objects, including interstellar candidates, flagged in real time. Among them, new comets will be tracked that echo the brightness patterns of 3 Atlas, and others that differ sharply. With each detection, automated systems will compare fresh light curves to the historical profile of Atlas, asking whether the new visitor brightens fades or fragments in familiar ways. If a comet shows a tail geometry, or isotopic hint reminiscent of 3 Atlas, it may be prioritized for deeper follow-up. If another object breaks every mold that at last helped establish that contrast, it will be just as valuable, widening the space of possible origins. Over time, the role of 3 at last will shift from active mystery to silent benchmark, a reference against which more exotic cases are measured. Students will study at last not only as a comet, but as an early demonstration of how a distributed network of observatories can pursue a single fleeting target. They will see how data from Mars solar probes and ground-based telescopes braided together into a method, one that Vera Rubin will extend across the whole sky. In that larger story, 3 at last becomes the first chapter of a much longer book, a reminder that visitors between the stars are not rare accidents but recurring opportunities. Forensic astronomy will grow by layering new arrivals atop the foundation, laid by at last turning isolated encounters into a statistically rich portrait of other planetary systems. Long after the comet has vanished into darkness, the questions it raised will remain guiding how we listen to the next faint messenger crossing the sun's distant frontier.